Good morning, everyone, and hello, everyone. Am I audible? Yeah, so in a very short time, we are going to welcome Dr. Anand Bhushan from NIT Patna. He is already with us online. So, yeah, welcome back after a short break.
Good morning, everyone.
Good morning, sir. Good morning.
Yeah.
Yeah, so please start your presentation. And I think I have already introduced the
Yes, sir.
audience about you, and I have
Yes,
given
sir.
a very brief introduction. So let's welcome Dr. Anand Bhushan, and it will be an exciting lecture like the previous.
Let
Yeah,
me start.
so Dr. Anand Bhushan, the stage is handed over to you.
Okay, sir. So good morning, all the participants. So this is the second lecture of the workshop. First of all, I would like to thank Dr. Somnath Sarangi to invite me for this lecture, and myself, Dr. Anand Bhushan, Associate Professor, Mechanical Engineering Department, NIT Patna. So MEMS is a technology of micro-sized devices made up of both electronic system and mechanical
Sir, your
deformable structure.
slides are not visible. Sorry,
That's
sorry,
not
sir.
visual.
No. Hey, Jitu, hello.
Yes, sir. Yes, sir. Yes, sir.
हाँ सर का स्लाइड दिख रहा है
No, sir.
हाँ ए कुछ
Let's one
ये
more
करो
time. Just try to
सेटिंग चेंज करो
Yeah, now it's visual.
हाँ नाउ
Yes,
इट
sir.
इज
Yes, sir.
विजिबल सर या
It's visual. Can you start?
हाँ एब्सोल्युटली फाइन सर या सॉरी सो प्लीज कंटिन्यू
Okay. So hope I am audible.
यस सर
Hello?
यू
Yes,
आर
sir. Yes,
ऑडिबल
sir. Audible.
एब्सोल्युटली
Yeah.
एब्सोल्युटली
So
ऑडिबल
let's start
Yeah.
from start. Okay. So this is a so my topic is the MEMS resonator devices. So MEMS is an acronym of micro electromechanical system, and it is a technology of micro-sized devices. It is made up of both electronic systems and mechanical deformable structure. So figure one, if we can see this figure one, it is a typical MEMS sensor module of a pressure sensor. So here in this figure, we can see that right hand side, there is a MEMS element. So MEMS element, it is made up of is a diaphragm, or we can say it is a thin plate, and it can deform when we apply some pressure on it. And the left hand side is electronic circuitry which is used to detect the motion and detect the motion of this diaphragm and tell us what is the pressure is actually is there. Okay, so MEMS has two important things. First is micromechanical elements, which are which is the deformable micromechanical elements are micro beams, micro plates, or micro comps, which we'll discuss later. What are these the mechanical and micromechanical elements are? As per concern or applications. So applications are it has many applications in different field like automotive, industrial automation, electronics, energy harvesting, and these applications based on the different components like sensors. So main sensor are MEMS accelerometer, gyroscope, pressure sensor, mass sensor. Accelerometer gyroscopes made up of inertial units, and it helps us to in a navigation of automobile or ships, and it can be aeroplanes. Accelerometer is a very important and most widely used sensor. It also used in automobile for the crash detection, just by if the crash is going to be happen, so it is a very large deceleration, and it detect, and it helps to deploy the airbag for the safety purpose. Similarly, gyroscope is another MEMS sensor which is also widely used in electronic industry. We use mobile phones, and we can see that when we tilt the mobile phone, the screen is also going to be tilt out. So this is the MEMS gyroscope is there, which detects the tilting of the mobile phone and give the signal, so the screen going to be changed. Similarly, the other components of MEMS are electronic components like filter, reference oscillator, and these are widely used for the RF MEMS. These are also known as RF MEMS, radio frequency MEMS, and help and used to build up electronic component in circuits. Other thing is the MEMS is also used as actuators like MEMS switches, digital micrometers, microvalves. Microvalves can be used in microfluidics. Digital micrometer is used for the image processing, and micro switch can be as an optical switch and used to be direct the lights all in the for different applications. We also know that we also heard the word nano electromechanical system. It is a further miniaturization of MEMS technology because MEMS and NEMS both share the similar electronic principle for actuation and sensing. So regarding analysis and all these things, both MEMS and NEMS have a very similarity. So specific components of the NEMS elements are nanowires, carbon nanotube, graphene plate. As we know that graphene plate is just a one atom thick plates, one atom thick layer of carbon, and carbon nanotube is just rolling of this graphene plate. We make a carbon nanotube. Similarly, we have a nanowires. So nanowires is just a 10-20 nanometer diameter and length of 1 or 2 micrometers. So these are the nanomechanical elements used as a mechanical component of MEMS devices. Regarding as an outline, so first we discuss the overview of MEMS resonator, and then we move toward the electrostatic actuation because the whole in the whole this presentation we particularly discuss one type of MEMS resonator that is known as electrostatically actuated MEMS resonators. And so after discussing the electrostatic actuation, we move to the micro beam resonator, which is electrostatically actuated. And then we can discuss the nanowire resonator, and finally we conclude the presentation. So first of all, first topic is the MEMS resonators. Okay, so first we start with the MEMS resonators with the different types of micro beams, which is actually fabricated and practically fabricated in industry and the experimental labs in different parts of world. And we can see that this figure 2, if we can see this figure is a SEM figure of a one of cantilever micro beam of just length 50 micrometers. And right hand side we can see this is a bridge type of a device which is shown is there. So this is of a length of 150 micrometer, and it is a doubly clamped micro beam resonator. Similarly, in bottom side, we can see this figure 3. It is indium arsenide nanowire oscillator of diameter 100 nanometer and length just 2.9 micrometer. So these are the types of micro and nanomechanical structures used in MEMS to operate it as a resonator or oscillator. So previous what we have seen that beams and these are the beams type of things which are simple structure, but much more complex structures also used in the much more complex structures are also used as a MEMS resonator. In figure 4, we can see this is a micro disc resonator. It is also suspended type of a diameter 150 micrometer. And figure 5 is a comb drive resonator. We can see it here in this figure. In figure 5, we can see this figure. They are the two parallel beams are there, and middle of that there's a comb drive is present. In comb drive, we can see that there are the two pairs of interlinked combs are there. One pair is attached to the micro beams, and other pair is a part of the fixed electrode. So when we apply some electrostatic bias DC voltage, so these combs attract each other and it make it to the deform these beams, or when we apply AC voltage, it is also oscillating. So this is known as micro comb drive type of resonators. Next, in MEMS resonator, we discuss its so as we have discussed that MEMS resonator has two aspects. One is the mechanical aspects, that is a deformable aspect which we discussed in previous slides. And second thing is the electronic systems. So the role of electronic system in MEMS devices are for the actuation and sensing. So in this slide, we can see it here, actuation. Here we can see that there are different actuation techniques which is widely used in the MEMS resonator. So first of all, if we see this is electrothermal actuation principle. In electrothermal actuation principle, we can apply large driving force and displacement. The basic principle of electrothermal actuation is that we have a suspended MEMS devices and we need to provide the temperature difference. How we can do it is, how we can provide the temperature difference? Actually, we can provide, we heat this temperature difference by providing electric current around the MEMS resonator, which heat up the MEMS resonator, and finally it made it to the deflect the MEMS resonator. Okay, so the basic advantage of this electrothermal mechanism is that it can provide a large driving force and displacement, but its response is slow. So if we try to oscillate the MEMS resonator with large AC voltage frequency, it cannot be possible. Second thing is that second method to actuate a MEMS resonator is electromagnetic way. In electromagnetic way, we have a beam type of MEMS resonator, and we provide AC voltage, AC current in this MEMS resonator, and this MEMS resonator is set up in a magnetic field. So what happens when the time varying current is passing through the beam, it generates Lorentz force, and this Lorentz force is also varying in nature due to the variation of AC current in the microbeam, and it provides the transverse force which made to deflect the microbeams. The other one more method is a piezoelectric. So in piezoelectric, so we use the piezoelectric properties to actuate a MEMS resonator. So how we can do this thing? One way is that in the microbeam, either we use a piezoelectric microbeam, or if not possible, we can put a layer of piezoelectric material on the microbeam. So as we know that the property of piezoelectric material is that when we provide some electric field in the piezoelectric material, it make it to be, it generates strain, and this strain used to deform the microbeam. So this is a very widely used method to actuate a MEMS resonator. It has very high sensitivity, and but the problem is that by providing the electric field, we cannot provide much more strength. So driving force and displacement per voltage is very small. The other is electrostatic way. So that, and this whole further the whole presentation is actually based on the electrostatic actuation principle. Electrostatic, what we do, we have a suspended microbeam and it is placed above a substrate. And what happened? We provide bias voltage between the substrate and the microbeam, and it will generate attractive electrostatic forces. So this electrostatic forces made it to deflect the microbeam. So it is very widely used and very high frequency response and low power consumption. So, in this presentation, we actually discuss electrostatically actuated microbeam resonator. So this is the primarily we're going to discuss. Next is sensing. In sensing, so again similar to the actuation, electronic circuits and electronic system is used to sense the motion of the vibrating resonator. So the principal way is a capacitive type. In the capacitive type, we measure the suspended microbeam and ground state can be made as a capacitor, and when the deformation is going to happen in the microbeam, which it changes the capacitance of system, and by measuring this change in capacitance, we can compute the deflection of the microbeams. Similarly, we can also use a technique of optical method to sense the motion of a microbeam resonator. Apart from that, there is a piezoresistive way. In piezoresistive way, what happened? We use the piezoresistive property. So we actually put a patches of piezoresistive patches on the microbeam resonator, and when there is deformation happen to the microbeam resonator, so this deformation change the resistivity of the piezoelectric material of the patches, and by measuring this change in electrical resistance of the material, we calculate the deformation of the microbeam resonator. So these are the sensing technique of a MEMS resonators. Next is electrostatic actuation. So as we discussed that, these are the overview we have provided what the MEMS resonator. Further we discussed one particular type of MEMS resonator which is electrostatically actuated. Okay, so the basic principle of electrostatic actuation is that we have a microbeam, and beneath that it is fabricated above a plate. So this plate is known as fixed electrode, and beam is a deformable structure. So these fixed electrode is one electrode, and beam act as a deformable electrode. And when we provide a bias DC or AC voltage between the beam and the fixed electrode, so there is an attractive force is developed which made it to deflect this beam. So in figure 8, we can see there are the one CAD model is provided here for the means rectangular cross section type micro beam resonator, and in bottom side we can see that we have a nano wire, nano electromechanical resonator as a nano wire of circular cross section. So this is another the right hand side we can see this is a circular cross section nano wire nano electromechanical resonator. So regarding responses, so as we know that bias voltage we can provide of two types. One is DC voltage and the other is a AC voltage. Figure 9 show the static deflection of carbon nanotube. Here we can see that we have a hanging cantilever type carbon nanotube from a tip, and 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 nearby we provide a voltage. In figure A, we can see there is when zero voltage. So so this nano wire is nano carbon nanotube it won't deflected. But in figure D, we can see that when voltage will increase to 40 volt, it get deflected toward the fixed electrode. We can see it. It is very visible. And similarly, figure 10, we can see that. So when we apply AC voltage, so what happens? So in figure 10, we can see that in figure A, there is a cantilever type carbon nanotube. And from nearby electrode, we provide AC voltage. When we provide AC voltage, what happens? In figure we can see that when we provide the frequency of AC voltage near to first natural frequency, so in figure we can see that the carbon nanotube is oscillating in first mode of natural frequency, that is for fundamental resonance. Same again when we provide the frequency of AC voltage near the second natural frequency. So in figure C, we can see that so the carbon the whole idea of providing DC voltage is static deflection, and which has application in switches, in micro switches and actuation of the and act as an actuator. But AC voltage, when we apply AC voltage, so we can operate a MEMS structure as a resonator or oscillator by applying AC voltage. So next we discuss the electrostatic actuation principle. So so what we have shown in early in the last slide, we can show that there is a micro beam, and which made it to deflect with the help of by applying a nearby electrode. So this particular principle we first discussed in detail in mathematically with a simplified model, which is in figure 1. We can see that in figure 11 is a schematic diagram of a parallel plate actuator. Here it is just a spring mass system which is placed near a fixed electrode, and here the mass is act as a movable electrode, and it is attached with the spring. This is a theoretical model. And make it to just understand what is electrostatic actuation. So in this spring mass system, this mobile electrode, that is a mass M, is the place is above a gap G from the fixed electrode. In equation 1 is provided the capacitance of this parallel plate system. Capacitance Cu is equal to epsilon A G minus U. It's a simple capacitance formula where A is the surface area of the mobile electrode and G minus U is the gap, instant gap of the between the mobile electrode and fixed electrode, because G is the initial gap and U is the displacement of mass M toward the fixed electrode. So effectively the gap between the fixed electrode and the mobile electrode is G minus U at any instant during the motion. In equation 2 show the due to this variable capacitance we get electrostatic actuation force. This electrostatic actuation force is the first derivative of the potential energy to half CV square. And when we apply the first derivative in direction of the displacement U, we get the electrostatic actuation force. So it is very clear in equation 2, the electrostatic actuation force is non-linear in nature. So effectively, the whole system is actually non-linear. So this is very important. And due to non-linearity, there are many specific applications of MEMS resonator we will discover. Now, equation 3 is the equation of motion. So, in equation 3, we can see in the left-hand side. So, it is the two terms. One is the inertia term, and other is the spring, and another is the potential energy. Another is the Ku. That is the spring force. So, this we can get it from the simple spring mass system. But right-hand side, it is the active force of electrostatic nature, and it is non-linear in nature. Okay. So this particular equation can be used to do both a static and dynamic type of analysis. But so in this whole in the whole lecture, we particular focus on the two type of characteristic. One is static characteristic, and other is a resonance frequency characteristic. What static characteristic is meaning is that when we apply DC voltage, so what is the deflection of the deflection of the mobile electrode is going to be happen. And secondly, the resonance frequency characteristic, its meaning is that due to the non-linear nature, when the mobile electrode is deflected, its resonance frequency is changes. So effectively, with variation in the DC voltage, resonance frequency is also going to be changed. So these two type of characteristics we discuss in detail. So in equation 4 is actually used for the static deflection study, that is static characteristic. In equation 4, we can get it from the equation 3 by just neglecting the time varying term, that is the del square U by del T square. Okay. So next is this equation 4 is just a non-linear algebraic equation. Here we are, and by solving this, we can get the function of US, that is the static deflection of mobile electrode, as a function of VDC. Next, equation 5. So when this mobile electrode is get deflected, after that at the deflected position, our objective is to calculate its natural frequency. For doing so, what happened? We define another variable UDT, and it is the displacement component apart from the static deflection. Okay. So this equation 5 we substitute in equation 3. And after that, we remove all the non-linear terms. So we get the equation 6. So if you see this equation 6, here these are two components. One is the inertia component and second is the spring component. So in spring component, we can see the coefficient of UD. If we see this provides the spring stiffness at the deflected position. And when we see this spring deflection equation, we can see simply that as we increase the DC voltage, this spring stiffness is going to be reduced. Now, so what the two equations we have just developed in the last slide, we just summarize it here as equation 7 and equation 8. Equation 7 is a nonlinear algebraic equation which we need to be solved numerically or analytically to find the relation between the DC voltage and static deflection. Similarly, equation 8 is a natural frequency at the deflected position. So later we see that so to non-dimensionalize these equation 7 and equation 8 will help us to better understand the characteristics of this parallel plate actuator. For non-dimensionalization, we introduce some non-dimensional variable as in equation 9. Here U, that is the displacement of mobile electrode, is non-dimensionalized with respect to G. That is G is the initial gap between the mobile electrode and the fixed electrode. Similarly, we also non-dimensionalize VDC voltage and omega D. Omega D is the natural frequency at deflected position. So we can see it here. Omega D cap is the dimensional natural frequency, and omega D is the non-dimensional natural frequency. So we non-dimensionalize with reference to the square root a by m, and it is simply the natural frequency of this MEMS resonator at zero deflection. Okay. So when we substitute these equation 9 in equation 7 and equation 8, we get the non-dimensional form of equation 7 and equation 8. Equation 10 is non-dimensional form of equation 7, and equation 11 is non-dimensional form of equation 8. So equation 10, we can see that, so the static deflection with respect to non-dimensional VDC voltage, we can get by solving equation 10. And similarly, equation 11 provides us non-dimensional natural frequency or at the deflected position. Now, the static characteristics. So here we can see that we have plotted the non-dimensional DC voltage and static deflection. So if we can see that as we increase the DC voltage, the static deflection is continuously increasing. But the nature is not linear. It is non-linear type. Here we can see that at higher DC voltage, for a small increment of DC voltage, in small increment DC voltage, static deflection is going to be increases very much high. So this is due to the softening effect of this parallel plate actuator, and we can also tell that this is the softening effect due to the electrostatic actuation force, because its meaning is that as the parallel plate actuator get deflected, when we apply some DC voltage, the overall spring effect is reduced. So that's why we tell it like that, softening effect. Now we can see in this figure, very important thing we can see in this figure, that when DC voltage is near to 0.5 or 0.6, that is the VPI square root 8 by 27, we can see that the slope of this curve is reaches to infinity. So what it's mean? Its meaning is that its meaning is that when we reach to the VPI is equal to square root 8 by 27, and when we increase this value slightly more than VPI, the parallel plate, that is the movable plate, is struck down to the fixed plate, and this is known as, this is a kind of instability exists in all electrostatically actuated MEMS devices, and this particular point is known as pull-in point. And the deflection at the pull-in point, we see that UPI is equal to 1 by 3. So it's meaning that we can operate a parallel plate actuator just a deflection from 0 to 1 by 3. It's meaning that 1 by 3 of the gap of initial gap between the parallel, that is the mobile initial gap between the mobile electrode and the fixed electrode, is the displacement trend where we can operate this parallel plate actuator. The second thing is a frequency characteristic. So this frequency characteristic is the plot between the non-dimensional frequency which we have just calculated and non-dimensional DC voltage. Non-dimensional DC voltage. Here we can see that the natural frequency is continuously reduced as we increase DC voltage. This is predictable because due to the spring softening effect, as we increase the DC voltage, the overall spring stiffness of this parallel plate actuator is reduced. So it's meaning that its natural frequency is reduced. So what happens? So effectively, its natural frequency reduces from 1, and at the pulling point, natural frequency is reached to 0 because it's so that it loses its strength of spring strength, and finally the plate, that is the mobile plate, strike down to the fixed plate. So this is the frequency characteristic, and in this frequency characteristic, we can observe one thing, that we can by changing the magnitude of DC voltage, we can vary the natural frequency of the system. So this has a very good application for the MEMS resonator, where we can change the system natural frequency by just varying the DC voltage after the fabrication. So usually many type of resonator, the frequency is always fixed and depend upon the system properties. But in the MEMS resonator, we had the opportunity to vary the natural frequency of the system. One other important thing is that pull-in has another very important aspect is this is the pull-in is a kind of stability, and it also decides the maximum DC voltage we can apply to the system. So it is important that to operate a MEMS resonator or NEMS resonator, we have to always keep the DC voltage much lower than the pull-in voltage. So we can safely operate the MEMS resonator. Next is a microbeam resonator. So what the electrostatic actuation principle we learned in the previous slides. Next, we apply these to a actual real case, that is a deformable microbeam. So figure 14 is a schematic diagram of electrostatically actuated microbeam resonator. Here we can see then blue, there's a microbeam is there. So it has a rectangular cross section of thickness H and width B. Thickness H and width B. So this and its length has a length L. So this microbeam is act as a mobile electrode and electrode plate, which is placed at gap G. That is the initial gap between the microbeam and electrode plate. So after that, we connect this microbeam and electrode plate with a voltage V. V has a both component DC and AC voltage. Further, this microbeam is actually has a boundary condition of fixed switch type. So this microbeam is actually actually have an end restraints. So there is always a chance of to build up of residual stress, and which is magnified as an axial load and in this figure. So the properties of this microbeam resonator has Young's modulus E, moment, surface moment of area moment of inertia I, cross sectional area A, damping coefficient C, rho is density and L is length. Okay. So here we can see that equation 1 is the non-differential equation which governs the motion of this microbeam resonator. If we see in the LHS has a 3 components. One component is the bending component, second is the inertia component, and third one is a damping component. So these always exist in any linear beam. But right-hand side is important. So the right-hand side, there are 2 components. One is known as non-linear beam stretching component. So what is this? Actually, this is known as geometric nonlinearity. When the microbeam is getting deflected, but due to the end restraint, these microbeam get stretched. So this nonlinear beam stretching component take care of the axial force build up due to the stretching of this microbeam, and it is a kind of geometric nonlinearity. And it is added with it is the initial axial load present due to the residual stress. The second one is a non-linear electrostatic force, which we have just seen that in the parallel plate actuator. This is also present. So effectively, a microbeam and electrode plate is the model as a parallel plate, where the instant gap at any point is a G minus U, and U as a function of x, that is the spatial coordinate of a microbeam. So this differential equation we will need to be solved to find the various characteristics of electrostatically actuated microbeam resonator. So again, for simplicity, we non-dimensionalize this nonlinear partial differential equation by introducing the nonlinear non-dimensional variable as provided in equation 2. Similarly, the deflection of a microbeam, that is U, is non-dimensionalized with respect to initial gap of the microbeam resonator. The spatial coordinate x is non-dimensionalized with the length L, and time is non-dimensionalized with the capital T, whose value is provided here. So this non-dimensional variable is substituted in our partial differential equation, and we will get equation 3 as a non-dimensional partial differential equation of motion. Here we can see that V is a voltage component, has a both VDC and VAC component. FU is the electrostatic actuation force component, electrostatic actuation force. So we need to solve this equation 3 to compute the static and frequency characteristic of microbeam resonator. So as we can see that this is an integral nonlinear partial differential equation, and it can be one way to solve this equation is the finite element method. Finite element method cannot or not only can able to solve this kind of equation 3, but when the MEMS structure is much more complex, like plate and some weird structure is also there, so finite element method can also solve these type of problems. But for the present case, it is just a micro beam and it is a simplified structure. So we can use another analytical method, analytical and it is a mixture of analytical and numerical technique, reduced order modeling. So we will use reduced order model technique to solve this equation 3, and we will later we show the characteristics of microbeam resonator with the help of the solution of reduced order model. So in reduced order modeling, we convert this integral partial differential equation as an ordinary differential equation. So let's see here. In reduced order modeling, first of all, we assume the form of solution. So here the assume the form of solution UXT, that is the displacement of a microbeam resonator as a multiplication of phi1x and U1P. Phi1x is first mode shape of a doubly clamped beam, and it is a standard and it is a standard function, and it is pre-known to us. The next thing is the displacement coordinate in the modal displacement coordinate U1P. So effectively, this equation 4 we need to substitute in our the governing partial differential equation, and after that we multiply the governing partial differential equation again with phi1x and integrate whole system from x is equal to 0 to 1. So due to this, finally we eliminate the phi1x term and will end up with just U1T term. So that finally we get the reduced order model at equation 5. So here we can see that in equation 5 it is reduced order model, and here U1T is the only dependent variable and independent variable time t. So it is a non-linear ordinary differential equation. So here we can see there is term K1, K3. K1 is just a linear, it is due to the linear bending of the microbeam. But K3 is a non-linear term. K3 U1Q is a non-linear term, and here the K3 is due to the non-linear stretching. And right hand side we again get FEU, V square FEU. FEU is the non-linear electrostatic actuation force. Next we discuss the static characteristics. So again, the equation 5, we just ignore the dynamic term U1 double dot and C1 dot. So we end up with the static characteristic equation, that is equation 6. Here we can see that equation 6 is again a nonlinear algebraic equation. Nonlinear algebraic equation which provides the deflection of U1S as a function of VDC. So we solve this equation in a MATLAB environment using F0 function, and we provide its result in figure 15. So the material which we have chosen is a silicon of length 400 micrometer, breadth 45 micrometer, and thickness 2 micrometer. The initial gap between the micro beam and the plate is just 5 micrometer. So we can see the deflection of micro beam. So here it is important to just note it there. So deflection we here plotted is the midpoint deflection of the micro beam resonator, and with respect to the voltage V. Okay. So it is a dimensional figure. So here we can see that when we apply the voltage, so it get the midpoint is get deflected similar to the parallel plate actuator. And again, we will get a pulling point. Again, we will get the pulling point as a instability similar to the similar to the parallel plate actuator. But one thing which we can note it here, the difference from the parallel plate actuator, in parallel plate actuator, the travel range of the parallel plate is just 1/3 of the gap. But here we can see the travel range of the micro beam resonator is the 3 micrometer, and it is about 60% of initial gap, that is 5 micrometer. So this is due to the presence of the geometric nonlinearity midplane stretching, which is missing in the case of a parallel plate parallel plate actuator of in the previous slides. So this is very important. So we can increase the travel range of a micro beam resonator when we have a doubly clamped bonding condition. Next is the frequency characteristics. So similar to the parallel plate actuator, here we substitute the we substitute the we present the displacement of the microbeam resonator in terms of static deflection plus U1S plus U1B. That is the displacement with reference to the static position, and we substitute in our reduced order model and neglect all the nonlinear terms. We end up with equation 7. So equation 7, we can see the coefficient of U1B is actually the effective spring constant of the micro beam resonator, and this effective spring constant, we can see that there are 3 terms. K1 is the case when the beam is not deflected, but other 2 component, one is positive and other is negative. The second component 3K3 U1 S square, it is due to the nonlinear beam stretching, and it has a tendency to hardening effect. Hardening effect, its meaning is that it tends to increase the natural frequency of the microbeam resonator. The next is the minus VDC square dou Fe by dou U1S. This component is actually the spring softening effect. So it reduces the natural frequency. So effectively, the natural frequency of this microbeam resonator is due to the interplay of the hardening effect due to nonlinear beam stretching and softening effect due to the nonlinear electrostatic actuation force. In figure 16, we can see the resonance frequency characteristic of this microbeam resonator. Here we can see that till 55 volt. So there is no much difference from the natural frequency, nearly same. So it is because the hardening and softening effect is both have a similar effect on the system. But later we can see that the resonance the first natural frequency is going to be increased. Its meaning is that hardening effect of the microbeam resonator dominating. But later, finally, the nonlinear electrostatic force is going to be dominate and make it to the pulling. So finally, the natural frequency reduces to the 0 at the pulling. Okay, next. So next, we provide the nanowire resonator. So nanowire resonator has one simple difference from the macro beam resonator is that the macro beam resonator has a rectangular cross section and nanowire resonator have a circular cross section. So effectively, we can see that in this slide, we can see that in figure 17, we provide just the schematic diagram of a electrostatically actuated cylindrical beam oscillator, and which act as a nanowire. So here beam is actually nanowire. So the equation are same. Equation 1 is the same. What we obtain in case of microbeam resonator, left hand RHS is same as a case of microbeam resonator. Right hand side nonlinear beam stretching again same, but nonlinear electrostatic force has a different function. So why it is? Because the capacitance formula for the case of a rectangular plates is different from the case of the circular beams. So that's why this formula. So the equation 1 is the equation 1. This nonlinear electrostatic actuation force is different. But apart from that, all things are same as a microbeam resonator. So again, in a similar fashion, we non-dimensionalize the equation and equation by introducing the by introducing the non-dimensional variables as per equation 2, and after that we get non-dimensional differential equation as equation 3. We solve it as the using the in MATLAB numerically. So here figure 18 show the static characteristics of a nanowire resonator. Here we can see that the static characteristics similar type of a microbeam resonator, but we can see there are the 5 different curves are there. So these 5 different curves are actually related to the different values of internal residual stresses. So when we have a compressive type residual stress, with the same voltage, we get much more deflection. And when we have a tensile type of residual stress, so we get for the same DC voltage, we get less deflection. And again, this is the resonance frequency characteristic. So again, we can see that resonance frequency characteristic for different values of the residual stresses. So we can see there when we change the residual stresses, we get the curve of the qualitative nature of this curve is going to be changed. For example, for the case when we have a tensile type of residual stress, we are getting or just decreasing type of resonance frequency characteristic. But when we have a compressive type of residual stress, we can feel that we have first the resonance frequency first increases and later it reduces to the 0. One important thing, there as is shown in the red, that is resonant frequency stability. So near the 36 volt, we can see there the effect of residual stress is minimal. Its meaning is that even the residual stress is going to be changed from compressive to the tensile type, but the variation of natural frequency is very low. So this particular characteristic we can use to develop as a new utility of non-linearity as high frequency stability of resonant frequency of a nano resonator or oscillator under operating temperature variation. So here we can see the figure that we plot the first natural frequency with different values of a normalized axial load. Normalized axial load is just a quantification of residual stress. We can see that for a different DC voltage, and when the DC voltage is 40 volt, we can simply, it is very clearly visible in this figure that when the DC voltage is 40 volt, then when the normalized axial load vary from minus 0.3 to 0.3, the natural frequency nearly same. So it will this nonlinearity in the system immune this nanowire resonator due to the variation of operating temperature, because variation of operating temperature build up additional axial stresses and has a capacity to change the natural frequency. But due to this nonlinearity, this is nearly stable. So this is the use of a nonlinearity in the MEMS or NEMS resonators. So now we conclude this presentation. So we can conclude that MEMS resonators have various applications as sensors, actuators, and RF elements. Reduced order model is suitable method which can use for simplified beam type of resonator to study the various physical characteristics of MEMS and NEMS resonator. As we have seen in this presentation, static deflection and resonance frequency characteristics. Next is pulling. Pulling is important instability exists in electrostatically actuated MEMS actuators and resonator, and it limits the function of the MEMS resonator. And finally, the electrostatic actuated microbeam resonators have very high frequency tunability characteristics, meaning that by varying the DC voltage, we can change the natural frequency of a microbeam resonator. These are the references we have used in this presentation, and thank you.
Okay, thank you, Dr. Anandabhushan, for such a exhaustive account of MEMS devices. And it is quite, I mean, I got a very good idea about what MEMS is and their mathematical model and all this. So now the floor is open for question. So please feel free to ask any question because it is a very interesting topic. Yeah, please. Audience. audience. Okay, so now, Dr. Anand, I'm having a few queries, and it is a kind of discussion. So now we
Yes,
look,
sir.
just look into this figure 16. So
Yes, sir.
over here, what I
Yes,
feel
sir.
is that if you are going to look into the parallel plate, so then the frequency
Yeah.
curve is a kind of, it is just going down, down, and down. But over here,
Down,
the
down. Yes,
up
sir.
is due to the your tension into the, I mean, the stretching device that you have used in
Yes,
the part. So that is why it is
yes,
building up.
yes,
Is
sir.
it so?
Yes, sir. Yes, sir.
Huh.
So
Yes, yes.
actually, equation
And
7, we can see it here. There are three K3 U1 S square. So as we go to deflect more, so it will provide the nonlinear stretching, and it has an effect of the increasing in the natural frequency.
yes. So it is just acting as a stiffening spring, strain
Yeah, yeah.
stiffening spring.
Yes,
Those
sir. Yes,
that strain stiffening effect is going to act. Now,
yes, sir.
when you are coming to the wire, so wire means you are giving, I have seen, I mean, it is my perception is that for a wire, if you are going to consider it as a string, if you model it as a string, then you cannot put the compression. Only tension can be given.
No, actually, what happened? We are not considering as a string. We are considering again as a beam, circular beam.
Okay. Only the thing is that the diameter is small, so that is why this electrostatic, this part is been instead of a parallel, which is a pretty simple. Now that
Yeah.
becomes complex due to the geometry, the
Yes.
electric forces which is coming, because over here the field directions are changing. So that is why which was quite simpler for the parallel plate. Now the field has changed, so that nonlinear function is going to come because of that.
Yeah.
Yeah, it is
Yeah.
good.
Due to the end boundary conditions, so because these are fixed in nature,
Yes.
so this particular nonlinearity comes into the picture.
Yes. It is a very informative, and I mean, we do actually. I'll tell to the audience is that whatever professor is talking about is done exactly for electro and magnetoactive material. So there is a huge similarity. So
Yes.
as you can see that he is talking about the pull-in instability. You'll find that in the next speaker, they are also going to talk about the pull-in instability.
Okay.
So
Yes.
it is just you'll find the actually it has been designed in such a way that we are going to say the same story, that our ultimate objective is to create one humanoid robot, and where all the I mean we have tried to get as much as possible the expertise into this field, and Dr. Bhushan has given us a huge information about this, and he has enlightened us with all these things. And we have seen in the previous speaker that she is talking about the micro level for the actuation of the muscle. You will find that the actuation is also through the electrical signal. And
Yes.
the immediate application of MEMS is that our car, I think we are having at least 50 such MEMS sensor, what he has talked
Yeah.
about.
There are lots of MEMS are now using automatives.
Yes, it is having more than 50. Even the, I mean, high-end cars, they will be having 70 plus. So that way, this his lecture is not important for the kind of this workshop, the theme of this workshop, but as well as the engineering application. So you are going to get a huge amount of thing. Now, Dr. Bhushan, I'll ask, I mean, I'll request you to go to the that COM part. COM you have talked about na in the initial COM
Home drive.
actuator. Yes, COM resonator.
Yes, sir.
Yeah. So this, sir, this one is a very interesting. Like it has a huge application to our each and everyday life, like in our mobile phone. If you are going to see our mobile phone, you'll find that this is there as an accelerometer sensor or as a gyroscopic sensor.
So actually, com dive is very much used. The one important thing is for a small range, it has some linear type of characteristics
Yes.
in actuation.
Yes. Yes. So it is a widely used. It is most
Yeah, it's
widely
very much
used.
used.
It is most widely used actuator or even sensor. So let us thank Professor uh, for his wonderful, exciting, enlightening lecture, and we have enjoyed a lot. So we'll be concluding this part. If you don't have any question, so please ask. Please feel free to ask any question. Okay, so if there be not
Okay.
any question, so we'll be concluding this session for the first half, and we are going to once again coming back sharp at 3 p.m. To listen Professor Prashant Saxena. And thanks a lot for your patience, and thanks Professor for his wonderful lecture. Thank you all, and we are going to meet
So I would like to
sharp
thank
at
sir.
3 p.m.
Thank you also sir for
Thank
inviting
you,
me
thank you.
for this lecture.
Thank you, sir. Thank you. Thank you all. So we are just logging off.
Okay, thank you, sir.
Thank you, sir.